Hello everyone. Welcome to our project measuring effectiveness of a drug using simple logistic regression model. This project is prepared and presented by Dibyagyothi Jena, ID B217015, Dharya Mehta, ID B217060, Akhilesh Patnaik, ID B217059.
Hi, I hope you're having a good time. I am Dibyagyothi Jena from ETC, and today I'm going to present my project, which is measuring effectiveness of a drug using logistic regression model. What our model does is that it can accurately predict the exact amount or the concentration of a drug that a patient needs in any given time. When you go to a doctor with some specific illness, the doctor, he's a human, right? He can consider only a handful of parameters, maybe 4 to 5 parameters at that time, but actual amount of parameters you need to consider is a lot. You need to consider your weight, your age, the type of illness you have, your family history, if you're resistant to certain medicines. So what our model does is it considers all of these parameters, and for an output it gives the exact amount of medicine that you need at any given point of time for that specific illness. Let's now take a look at what logistic regression is. Regression, in simple terms, is the relationship between a dependent variable and many independent variables. Logistic regression is a type of machine learning model which uses the sigmoid function, and here's the graph of sigmoid function. When theta is greater than 0, the value of let's say y, let's say this is y. If theta is greater than 0, the value of y is greater than 0.5, and if theta is less than 0, the value of y is less than 0.5. And this can be used as a deterministic model to say if the probability of something, of an event to happen is more than 0.5 or less than 0.5. If it is more than 0.5, we can consider the Boolean value as 1, and if it is less than 0.5, we can consider the Boolean value as 0. Here in our case, 1 represents that the drug or the medicine is effective, and 0 represents that the drug is non-effective. For a patient, here are the kind of parameters that you can set. The parameters are age, weight, illness, resistance to certain drugs, and family history. There can be many more parameters which will depend on the type of illness that you have. The coefficients that you see here attached with these parameters are called the weights. Weights are simply numerical importance given to each parameter. In this model, the weights have to be manipulated again and again with each training example to make our prediction more accurate. As you might have guessed by now, theta is the dot product of two vectors, the parameter vector and the weight vector. The data that we use in this model has two parts, training set and testing set. The training set is again comprised of all these parameters which compute to give a result y0. The testing set is used to validate or test our model. Again, the logistic regression function or the logistic regression model has a cost function which is simply the error function. Or you can also call it the entropy function. Our aim now is to minimize this error and update these weights such that the final prediction can be as accurate as possible. And how do we minimize the function? We take its derivative and equate it with 0. Let's consider only one parameter, alpha. Here we can see in this equation, we are updating alpha continuously with each training example. The learning rate here decides how quickly and how accurately you can minimize the cost function and hence optimize the model. Here is, let's say, a graph of the cost function, and this is the minimum value of the cost function that can be achieved. If the learning rate gamma is too high, and suppose for any theta 1 in this point, if the learning rate gamma is too high, the solution to this problem will overshoot and will never reach the optimum value. If the learning rate gamma is too low, if it is much lower than the optimum value, then the accuracy will be very high, no doubt, but the model will take a lot of time to train, going through the entirety of this curve to reach here. Now this method is repeated for all of these weights in a loop for each training example, so that all these weights will be optimized, and in the end we can have a prediction that is as close as possible to the real answer. To implement this model, we had a very simple experiment lined up with an Arduino Uno and an alcohol sensor. Here we detect the concentration of alcohol and if that amount of alcohol will be effective on a person or not. Since we did not have any data, we have randomly chosen our own data and randomly assigned the parameters as well as the values. This is just a proof of concept to show you that the model will actually work when real data is given and tested on it. For this experiment, the blue graph gives the concentration of the alcohol and the red graph gives the probability if that much amount of alcohol is effective or not. As you can see, at some particular point, both of these graphs intersect. If we increase the concentration a little bit towards the right, or if we move towards the right, the probability that the amount of alcohol is effective becomes 1. If we decrease the concentration a little bit, the probability becomes 0. As you can see, there is a drastic change in probability at this point, which means beyond this point we do not need to administer more drug, since the probability is already 1 and the drug is already working. If the concentration is below this point, the probability of working of this drug is 0, and hence it shows that we need to increase the concentration a little bit more till the probability becomes 1.